Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh and very good afternoon to all. On behalf of University Technology Malaysia, I would like to welcome all viewers to the 110th Professorial Inaugural Lecture Series by our respected speaker, Professor Engineer Dr. Sahmah bin Mohd Supa'at, Chairman Research Alliance in Innovative Engineering. This event is brought to you live through Faculty of Engineering's Facebook and YouTube channel. The title of today's lecture is very interesting and timely indeed, which is Photonics, Eliminating Electronics Bottleneck. I'm Nadiatul Huda Zulkifli, your MC for today's event from the School of Electrical Engineering. First and foremost, let's thank Allah the Almighty for this opportunity, and let's begin with Surah Al-Fatiha as we seek for His rahmah and blessings to our program that all of us will get benefits from it, insyaAllah. Al-Fatiha. Okay, before we start, just a quick reminder for viewers to fill in the attendance form pinned in the comment area. Next, to mark the opening of today's Professorial Inaugural Lecture Series, I would like to invite the Honorable Chairman, Professor Technologist Dr. Ruzairi bin Abdul Rahim, Dean of Faculty of Engineering UTM, to give his opening remarks and biosketch recital of our speaker. Over to you, Prof. Ruzairi.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh and salam sejahtera. Okay, I will give some introduction about my friend, Professor Engineer Abu Sahmah. Okay. Professor Engineer Abu Sahmah bin Mohd Supa'at has served at UTM since 1986 after completing his first graduate degree in Bachelor of Electrical Engineering, majoring in Communication Engineering at the Faculty of Electrical Engineering, University Technology Malaysia as Assistant Lecturer A. He earned a master's degree in 1991 and a PhD in 2004 in optical communication and photonic switching, respectively from the same university. He is currently the chair of Innovative Engineering Research Alliance under the Department of the Deputy Vice Chancellor, Research and Innovation. He has served as a chair since 2013. Prior to this appointment, he served as Deputy Dean of Development for 5 months and Head of the Department of Telematic and Optical Engineering for 3 terms at the Faculty of Electrical Engineering. In addition to administration, he also responsible for teaching and also doing research. He has taught various undergraduate and postgraduate courses. To date, he has overseen more than 100 undergraduate and 20 postgraduate student projects, which is acquired expertise in photonic switching, devices, and networks. His research findings have been translated into several publications, with Scopus H-index of 17. To date, he has written more than 100 journals and published in the ISI and WOS journals indexes, of each in Q1, Q2, and also Q3. He has also contributed more than 150 articles that have been published in national and international journals and proceedings of this. He also had the opportunity to publish a book entitled Principles of Communication by Person Malaysian Sendirian Berhad, 4 monographs entitled Electromagnetic Field Theory and Theory of Electromagnetic Field Solutions in Malay and English for students of electrical engineering undergraduate, and 25 book chapters were published by UTM. He has also managed to get 1 patent granted and 15 patent filed and holds 6 UTM copyrights. At the international level, external parties have cordially invited him as a visiting professor at City University, Hong Kong, and Busan National University, Korea, as well as one manufacturing company of photonic devices, Chem Optics of Korea, to share his research findings in the area of photonic switching and integrated optics. He has been appointed as steering committee of ICT Virtual Organization of ASEAN Institute and NICT ASEAN IVO, which is a global alliance of ICT and R&D institutions and university in the ASEAN region and Japan since 2015. At the national level, due recognition are also given and appointed as a committee member to Pelaburan Dana Awam, R&D CNI, RMK12, Bahagian Industri Pembuatan, Sains and Teknologi, Unit Perancangan Ekonomi Jabatan Perdana Menteri. He has also as committee member of IEC National Committee, Ministry of International Trade and Industry, MITI, Technical Committee on Nanotechnology, Standardization for Electrical and Electronic Products and Systems in CIRIP. He also committee member of Expert Evaluation and Technical for Strategic Research, SR, under Ministry of Science, Technology and Innovation, MOSTI. And also the committee member of Evaluation of Ministry of Higher Education on the research grant such as FRGS, LRGS, TRGS, and PPRN. He has also been appointed as external examiner for PhD at 2 foreign universities and 15 at domestic university. He also has been appointed as a judge for several projects R&D exhibition conducted by MIMOS, Telecom Malaysia Research and Development, and USIP. As a qualified professional engineer with a practicing certificate, is one of the members of the Board of Engineers Malaysia accreditation panel for undergraduate engineering programs conducted by government and private universities in Malaysia. He has also been appointed as an external evaluator for the undergraduate engineering program for the Faculty of Engineering at UNIMAP UMP, and also to date for the Photonic Engineering and Electrical and Electronics Engineering program, respectively. He has also been appointed as the external evaluator for the promotion of professor and associate professor for several universities in Malaysia, namely UKM, UPM, USIM, UTEM, UIAM, UNIMAP, and also UMP. In addition, MOSTI, MOHE, industry, and the university have realized his expertise by providing long-term and short-term grants as project leader for 24 projects, totaling more than 9.4 million, and co-researchers for 27 projects, totaling more than 8.3 million. By securing the grant, he and members of the research group have successfully expanded the Light Wave Communication Research Group, or LCRG, and their research lab by acquiring specialized equipment and have gained significant experience and technical knowledge in the areas of human capital and expert development. So far, there are 10 of his PhD students who have graduated as the main supervisors. He was also honored with national and international recognition for product invention that included 5 gold, 5 silver, 5 bronze medal, and a jury awards. In addition, he has patented 5 products as a principal inventor, 11 products as co-inventor, and more than 6 intellectual property copyrights. He was also given the opportunity to deliver his expertise as a keynote address, invited and plenary lectures in his area, as well as appointed as an evaluator for papers to be published in the reputed journal of ISI and WS, such as IEEE Sensor Journal, IEEE Photonic Journals, Optical and Laser Technology, and also Optical Fiber Technology Journal. So that's all for introduction for Professor Dr. Abu Sahmah, and personally, I hope that we all will enjoy and get some benefit from this talk today. Assalamualaikum warahmatullahi wabarakatuh.
Okay, Alhamdulillah. Thank you very much, Prof. Uzairi, for the very insightful opening remarks to Prof. Abu Sahmah's outstanding achievement at both national and global levels. To the viewers, I would like to welcome you all to leave your feedbacks and questions in the Facebook comment area. Okay, let's now go to the highlight of today's program. Without further ado, I would like to invite Prof. Engineer Dr. Abu Sahmah to deliver the much anticipated Professorial Inaugural Lecture. Okay, over to you, Prof. Abu Sahmah.
Bismillahirrahmanirrahim. Alhamdulillahi rabbil alamin wassalatu wassalamu ala asyrafil anbiya wal mursalin wa ala alihi wa sahbihi ajma'in. Rabbi shrah li sadri wa yassir li amri wa hlul 'uqdatam min lisani yafqahu qawli. Thank you to the Master of Ceremony, Associate Professor Engineer Dr. Najiatul Huda Zulkifli, Chairman of my Professorial Inaugural Lecture today, Professor Technologist Dr. Rozairi Abdul Rahim, Dean of Faculty of Engineering, University Technology Malaysia. My commentator for today, Professorial Inaugural Lecture, Professor Engineer Dr. Sivia Madaliza Idros, is my colleague in the Lightwave Communication Research Group, LCRG. Professor Engineer Dr. Muhammad Wazir bin Mustafa, Chair of School of Electrical Engineering, Dr. Asrul Izam, my Head of Research Group, Lightwave Communication Research Group, to all my colleagues in LCRG and the School of Electrical Engineering, my colleague in the Faculty of Engineering, and all my colleagues and friends in the University Technology Malaysia, also friends from other universities, industries, my students, and my ex-students from all over the globe that has been given the opportunity to attend this inaugural lecture. I've chosen the title for my professorial inaugural lecture today as Photonics, Eliminating the Electronic Bottlenecks. I hope that this professorial inaugural lecture will give benefit to all of us. And first of all, I would like to take this opportunity to acknowledge the management of the School of the Electrical Engineering, where I belong, and have been working in the School of Electrical Engineering under the Communication Engineering Department since 1986, and the Office of Research Alliance under the Department of Deputy Vice Chancellor, Research and Innovation, UTM, where I've served now since 2013. Also, the management of the Department of Deputy Vice Chancellor, Academic and Internationalization, UTM, that organized this inaugural lecture today. As mentioned earlier, that the title of my sharing for my professorial inaugural lecture is Photonics, Eliminating Electronics Bottleneck. So in the context of the communication engineering field, photonics is something to do with light, with the particles named photon, with no mass that travel with the speed of light. And on the other hand, the speed of an electron can be zero or anything under the speed of light, depending on the method the electron travel. And therefore, it is impossible for an electron to achieve the speed of light. This is what has been written on the main entrance gate of UTM, the verse of Al-Quran, Surah Taha, ayat 114, and Surah Al-An'am, ayat 132. Rabbi zidni ilma, my Lord, increase me in knowledge. Walikulli darajatun mimma amilu. For all there will be degrees or rank according to what they did. And these verses should remind us, especially for the students who enter the university, that is the knowledge-based ivory towers, the place of knowledge to explore. And of course, we need to ask Allah subhanahu wa ta'ala the zeal to continue and to seek and constantly add knowledge in the field of study. And inshallah subhanahu wa ta'ala will surely increase the rank of knowledgeable people and will reward according to what they did. This surely goes beyond just the intellectual quotient, but more important is to grow spiritually closer to Allah subhanahu wa ta'ala, the creator, and finally for achieving the Jannah of Allah subhanahu wa ta'ala. So ladies and gentlemen, the outline of my sharing today is the introduction of photonics communication, my research focus, photonics devices and photonic networks, research option, and the conclusion toward future likely attributes of the next generation network. To start with, for better understanding, we would like to ask first, what does photonics means? Photonics is an area of study that involves the use of light, whose fundamental element is the photon. Photonic application use the photon in the same way that electronics application use the electron. For the devices that run on light have several advantages over those that use electricity. This will be clearer and much more appreciated about the topic that I presented today when we move on, inshallah. It is just my analogy. Because of the electron, it becomes electronic. Similarly, because of the photon, the fundament, it becomes photonics. So in the electronic system, the fundamental particles that carries information is an electron. That is the movement of the negative charge called electron in the system. That is why they name it as electronics. Similarly, in the photonic system, the fundamental particles that can carry information are the photon. So their name is photonics. So how fast does light travel? Light travel at a speed that nearly 300 kilometers per second, or 3 times 10 to a power of 8 meter per second. So at that speed, light takes 1.3 seconds to reach us from the moon and 8.32 minutes to reach us from the sun. So how can we measure the speed of light? So we can measure the speed of light with a very simple apparatus in the laboratory. So we need to have a pulse generator, light sources as a helium neon laser, mirror, and the detector, such as positive intrinsic negative diode, and the oscilloscope. So the speed of the light can be calculated by the distance of light travel, in this case 10 meters, and divide by the difference of the light detected at the time taken at t equal to 0 meter, and the time taken after the light traveling of 10 meter. So the time is 33 nanosecond difference. Therefore, the speed of the light is distance divided by time. So in this case, 10 meter is divided by 33 nanosecond, equivalent to 3 times 10 to the power of 8 meter per second. So the early researchers is Ibn al-Haytham, who lived in 960 to 1040, known in the West as Al-Hazin, is referred to as the father of modern optics. He made significant contribution to the principle of optics. His most famous is the book of Optics or Kitab al-Manazir, which was translated into Latin and became very influential. He laid out completely new ideas about the light and vision in this book he wrote in the year 1011. These are the characteristics of light, and the very important characteristics of light is an electromagnetic wave and falls in the electromagnetic spectrum, and therefore the frequency is very high, up to the terahertz region. So in communication engineering, data rate or speed is proportional to frequency. So this is the electromagnetic spectrum. My research focus is at the near-infrared window of the electromagnetic spectrum, ranging from 700 nanometer to 2000 nanometer wavelength. That covers the first telecommunication window, the second and the third telecommunication window, which correspond to the optical frequency ranging from 180 to 210 terahertz. First telecommunication window is concentrating at the center of wavelength at 800 nanometer wavelength, and the second telecommunication window at 1300 nanometer, and the third telecommunication window at 1550 nanometer wavelength. Well, by now, all the telcos company working in this window as a center of frequency. This is because at this window, fiber optic attenuation loss is very low at 0.2 dB per kilometer. So in the telecommunication system, what we know, the media to carry information is like air or atmosphere, twisted pair cable, copper wire, and waveguide. But for light, special media is needed. That is optical fiber, made of glass, but pure glass like silica. Basically, silica is derived from sand, which is a raw material but requires the additional purity of silica glass to form an optical fiber. This picture shows the diagram of a copper cable and fiber optics. The choice is very clear from the comparison of optical fiber and copper wire or coaxial cable. We can see from the item list for comparison, the optical fiber outperform the coaxial cable in all aspects. The most important parameters are cost, energy, bandwidth, and security. And then the size of the optical fiber core is less than the size of the common diameter of the human hair. For human hair size is 70 micrometer. The most common optical fiber used in communication system is a single mode and multimode optical fiber. For single mode fiber, the core size is 8 to 9 micrometer, and for the multimode fiber, the core size is 50 to 62.5 micrometer. So in the 1970s, the fiber length that can be fabricated is up to 1 kilometer because of the high attenuation loss. And today, we can have a fiber length up to 100 kilometers after the reduction of attenuation of loss 100 times due to the maturity of the fabrication technology and the purity of the material used for the optical fiber. We can see from the graph there that the wavelength of 1550 nanometer is the lowest attenuation loss of 0.2 dB per kilometer, which also represents the third telecommunication window where all the telcos companies are now working at. The first window is at 900 nanometer and the second window is at 1300 nanometer. We can also see the compositional fluctuation loss due to the Rayleigh scattering, absorption, and intrinsic losses from 700 to 1700 nanometer wavelength of materials in the silica fibers. This is the common example of internet broadband connection that works through copper wires versus fiber optic cable. For example, using ADSL, asymmetric digital subscriber line, the downloading is up to 10 megabit, whereas with the fiber optic can go up to 100 megabit. Of course, you can have more using fiber optics, up to gigabit, but then you have to pay more. This graph showed the capacity of the information versus yield for the transmission medium. For example, twisted pair cable, coaxial cable, and the microwave system. We can see the optical fiber just emerged in the 1960s and will continue to dominate in the telecommunication system as the amount of the information capacity that it can support in the future up to terabit per second with the TDM, time division multiplexing, and the WDM technology, wideband division multiplexing technology. So therefore, there is no doubt that the photonics is the enabling technology for high-speed communication. Photonics is the science of generating and harnessing light. Photonic communication will overcome the electronic bottleneck where the demands of huge and fast carrying the information are in the tremendous growth in the field of a telecommunication system in the future. So the impetus of the modern photonic communication was laid by Charles Cow. And when he first discovered dielectric waveguide in the 1966 for broadband communication, and the optical fiber is started to commercialize in the 1970s by the Corning and AT&T. And he was the Nobel Prize winner in physics in 2009 for groundbreaking achievement concerning the transmission of light in fibers for optical communication. So in 1990, single mode fiber, data rate of up to 622 megabit per second. And now the capacity is around 1 terabit per second with a data rate of 100 gigabit per second. And this is the structure of optical fiber consisting of a core, cladding, and buffer coating. The waveguide structure can also be fabricated in the form of the slab as a planar waveguide and the channel waveguide, such as embedded, strip-loaded, ridged, and buried waveguide. Why photonic switch device? So the original goal of all the optical network was based on keeping the data signal entirely in the optical domain, from the source to the destination, to eliminate the so-called electronic bottleneck or transparency. There will be no more conversion of an optical signal to electrical and back again to optical. Therefore, the need for a photonic switch is indispensable to support the explosive growth of network traffic and high bitrate transmission capacity. For example, for 100,000 subscribers, digital exchange to transmit one voice channel in digital form, it needs 64 kilobit per second for each subscriber. So for 100,000 subscribers, the estimated aggregate switching capacity is 10 gigabit per second. So with the explosive growth of traffic demand at this now, which includes the data, voice and video, it needs a minimum 155 megabit per second for each subscriber. And therefore, for 100,000 subscribers, the estimated aggregate switching capacity is 15.5 terabit per second. This can only be supported with the photonic switching that can provide such capacity. Again, with the increasing number of ports and users and the demand for higher data, rates and speeds, electronics will find their limitation. In the all-optical system, the application of photonic switches are provisioning, protection, reconfiguration, restoration, network monitoring, circuit switching, and packet switching. For the current network, the photonic switch is in the range of milliseconds, and for the next generation network, the switching speed will exceed less than 1 microsecond, together with the other performance of figure of merit of low insertion loss, low crosstalk, and high capability. So in this research work, we are using polymer material for the development of our photonics devices. To be more specific, we are using thermo-optic polymer material due to the cost of the material. Polymer is a raw material, and all polymers have thermo-optic coefficient, with the figure of merit which is comparable with the 3-phi semiconductor materials. The advantages of polymer material compared to gallium arsenide and titanium lithium niobate is easier fabrication process, and that leads to develop optics devices with significantly lower material production and cost. And these are some of the photonic switch configuration that has been explored in the research study that is based on the Y junction, DC directional coupler, MMI multimode interference, and MZI Mach-Zehnder interferometer. So the polymers that have been used are the ZPU series of polymers that have a closer index of refraction matched to the optical fibers for various waveguide design structure. The most important is that we can blend this polymer, or in other words, is that the refractive index tuning, where we can tune the refractive index as close as possible to the refractive index of the optical fiber for both transverses of electromagnetic field, that is TE or TM, transverse electric or transverse magnetic. Also, we can get a good range of refractive index tuning from 1.4 to 1.7, so that we can adjust the diameter size of the core for the waveguide to be designed, be it symmetrical or symmetrical waveguide structures, so that it can match the diameter size of the single mode fiber for practical application. So directional coupler is the very basic, most common structure as a building block for photonic coupler and photonic switch. It consists of 2 input straight waveguide, 2 input S-band waveguide, a coupling region, 2 closely spaced parallel waveguide, 2 output S-band waveguide, and the 2 output waveguide. So the amount of energy transfer can be set from 0 to 100% by adjusting the waveguide separation and interaction length of the coupling region. Therefore, directional coupler can easily provide any desired splitting ratio. This is the cross-section of the proposed structure for a 2x2 directional coupler photonic switch as a building block for larger switching matrices in the photonic networks. The core is the buried square waveguide. For symmetrical structure, the surrounding or the lower and the upper cladding of the core has the same refractive index. For the asymmetrical structure, the upper and lower cladding of the core had a different refractive index. As shown in the schematic diagram, the optimization has been carried out for the coupling length variation as a function of the waveguide dimension, waveguide gap, and the effective index difference between the core and the cladding layers. Optimization also has been carried out for the positioning of the electrode heater, which maximize the effective index differences between branches at the two parallel waveguide at the coupling region. And this is the standard foundry services or fabrication process involved for the development of photonic device using polymer materials, and also compatible with the fabrication process of 3-5 semiconductor materials for passive components such as photonic couplers or combiners based on the waveguide. For the active components such as photonic switches, we have to proceed with the fabrication of heater electrode and pads. The standard process involves silicon wafer preparation, spinning of the waveguide core, layer, lower and upper cladding layers, photoresist, lithography, etching process, and aurum plating process. This is the experiment setup for the device under test characterization, DUT. We can see the image after the magnification factor of 100 times of the single mode waveguide arms with the heater electrode and the heater pads, which was nicely developed on the silicon wafer. The near field patterns of the fabricated switch show the cross state, bar state, and the 3 dB couplers. So the switching curve shows that when the light is launched at the input port of P1, the crosstalk at the cross and bar state is 29.4 dB and 32.7 dB, respectively, with the switching power of 15 milliwatt. When light is launched at the P2, the crosstalk at the cross and the bar state is 29.43 dB and 33 dB, respectively, with the switching power of 12.87 milliwatt. And the measured switching time is 5 milliseconds. Next is the digital optical switch, or DOS. The switch is composed of two interacting waveguide arms through which light propagates. In principle, a signal switching from the input port to one of the output branches in DOS is a result of the refractive index difference between branches in a Y-branch single-mode optical waveguide. The change in the refractive index may be induced by applying a voltage to the selected section. The figure shows a schematic view and the specification of the proposed structure of DOS, where a new digital optical switch with a large branching angle and short device length exhibit low crosstalk and low power consumption. The Y branch shape was optimized by introducing constant effective refractive index difference between branches, delta N effective, along the propagation direction to provide decreasing local branching angle that result in the improvement of the crosstalk. Two modified cosine band was introduced to form the Y branch. The modified cosine band was then connected to a linear branch. The heater electrode was optimized based on the parabolic structure so that the temperature fields induce a constant delta N effective to satisfy the initial assumption in designing the Y branch shape. So this is the cross-section of the proposed structure of the DOS. It consists of a buried square core waveguide of 7 by 7 micrometer for single mode operation, and the heater electrode positioned on the top of the upper cladding layer, and the scanning electron microscope fabricated image after the magnification factor of 100 times of the 1/2 waveguide structure. So the switching curve shows that when the heater pad 1 is on, the light is at P out 2. The crosstalk is 45 dB, insertion loss is 1.8 dB, and the switching power is 56 milliwatt. And when the heater pad is on, the light is at P out 2, P out 1. The crosstalk is 47 dB, insertion loss is 1.8 dB, and the switching power is 56 milliwatt. So the measured switching time is 4.8 millisecond. Next is the MMI switch, multimode interference switch. So multimode interferent MMI couplers have attracted considerable interest due to their unique characteristics such as compactness, relaxed fabrication tolerance, large optical bandwidth, and polarization insensitivity when strongly guided structure are used. Consists of single mode and multi-mode section and applicable in splitters and combiners, mode converters and power splitters with arbitrary splitting ratios. It is based on the self-imaging in multimode waveguide where the input field is reproduced in single or multiple images at periodic intervals along a multi-mode waveguide. So the figure shows a schematic view of the MMI proposed structure and the cross-section at AA prime, BB prime, and CC prime. So new 2x2 thermo-optic MMI switch where only one heater electrode is used with two trenches. The first trench is the air trench in the highest layer, and the second one is the silicon trench in the lowest layer, which expand from the silicon substrate to the lower cladding at the center of the MMI coupler and between two self-image areas. The 2x2 MMI photonic switch with a strong guiding rich waveguide with high lateral index contrast due to lateral air interface and high transverse index contrast, delta N equal to 0.05 between the core and cladding regions. The core layer of ZPU12480 with a refractive index of 1.48 and thickness equal to 1.5 micrometer surrounded by upper and lower cladding region of ZPU430 with a refractive index of 1.43. So the simulation for the temperature distribution was done using finite element method for the MMI multimode interference switch. It can be seen that the temperature distribution is blocked significantly by the air and silicon trenches. The silicon trench provides a thermal bypass path. It has a high thermal conductivity, which is acting as a heat sink, and the heat transfers through the silicon trench to the silicon substrate. Figure A, in the absence of the applied power on the heater, light coupled to the first input waveguide is emitted from the second output waveguide that is at the cross state. Figure B, when a pi phase shift is applied, heater electrode is on, light coupled to the first input waveguide will be imaged onto the first output waveguide that is at the bar state. So the switching curve shows that the crosstalk of MMI switch without silicon trench is minus 33 dB and minus 25 dB at cross and bar state respectively. So crosstalk of MMI switch with silicon trenches is 33 dB and minus 31 dB at cross and bar states respectively. Increase and better by 6 dB at the bar state with silicon trench. So the switching power for both switches is 1.42 milliwatt, and the switching response for both switches is 1 millisecond. Figure shows a schematic of MNZI and integrated MMI with MZI switch. Mach-Zehnder interferometer has two input ports and two output ports. A basic MZI is constructed using two couplers, one at the input acts as a splitter and another at the output acts as a combiner. The light is split in two arms of the interferometer by the input coupler and recombined at the output by the output coupler. MZI can work as a modulator, switch, isolator, wavelength multiplexer, demultiplexer, and etc. Next is the schematic view of the MMI MZI proposed structure and the cross section at the AA prime, BB prime, and CC prime. The configuration of 2x2 MMI MZI consists of an MZI with two 3 dB MMI couplers and two straight parallel waveguides between them. So the light is launched using 2.5 micrometer wide input output waveguides. The length of each MMI coupler is set to 3 L pi over 2, where L pi corresponds to the bit length, and the width is chosen 8 micrometer. The MMI MZI photonic switch adopted a rich type waveguide. It consists of a core layer of ZPUs 12480 with a refractive index of 1.8 and thickness 1 micrometer, surrounded by upper and lower cladding region of ZPU 13430 with the refractive index of 1.43. The structure is considered as a strong guiding rich waveguide with high lateral index contrast due to the lateral air interface and high transverse index contrast, that is 0.05 between the core and cladding region. Next is the finite element simulation of steady state 2D temperature profile and the heat flux of layer structures A without silicon trench and B with silicon trench. As shown in A, without a silicon trench, the heat will transfer to the second waveguide. Figure A, in the absence of the applied power on the heater, light coupled to the first input waveguide is emitted from the second output waveguide that is at the cross stage. Figure B, when a pi phase shift is applied, that means heater electrode is on, light coupled to the first input waveguide will be coupled onto the first output waveguide that is at the bus stage. Also, the finite different BPM, beam propagation method simulation, shows that the MMI MZI switch crosstalk is minus 33 dB at the cross and minus 31 dB at the bus state with the switching power of 1.5 milliwatt. Next shows the experimental results of the MMI MZI switch, showing the near field patterns in the cross and the bus stage, and the wavelength dependent loss and the polarization dependent loss within the C band, that is from 1530 to 1565 nanometer, which give below 1 dB values for both switching states. A detail of the experimental results of the MMI MZI developed photonic switch give low switching power of 2.2 milliwatt and the crosstalk at the two state of less than 31 dB and the switching speed of 0.7 millisecond with the extinction ratio of 31 dB, PDL of less than 0.3 dB at third telecommunication window, WDL with length dependent loss of less than 0.88 dB over C band, good performance within C band with the vacillation of the insertion loss value around 0.88 dB. And this photonic switch can find application for optical path provisioning and restoration, optical path protection, dynamic variable optical power distribution, and optical cross-connect. This is the example of the schematic diagram of the hardware architecture with centralized monitoring for providing protection and restoration against fiber failures or faults in the distribution region of passive optical network. The protection switch device is employed at the customer end just before the optical network units, ONU, to ensure the data flow continuously due to the breakdown occurs in the network and instantly repair operation. So the need for photonic access network is due to tremendous growth in both backbone and metro access network capacity, and users are becoming more sophisticated with rich multimedia, real-time services, and the last mile remains a bottleneck. Current last mile capacity has increased from 56 kilobit per second, that is dial-up modem, to a few megabits per second cable modem or digital subscriber line, DSL connection, still far short of the gigabit line speed services. So copper-based access network will soon no longer be able to meet the ever-growing consumer demand for bandwidth. Passive optical network-based system as considered possible successors. The two most viable architectures is single channel time division, multiplexing PON or TWDM-PON, and multi-channel wavelength division multiplex PON or the WDM-PON. So the challenges for the future access network of PON: bandwidth requirements, demand for higher bandwidth and high quality of services, must achieve high capacity and good scalability in terms of link range and number of users. Most telco services providers already invest multi-million dollars to deploy PON system, for example, Ethernet PON and Gigabit PON in their network. So to maintain the investment of the current network, the evolution of PON towards next generation PON must be able to coexist with the current EPON or GPON. There are some of the characteristics of PON. As it names, there will be as many as possible no active devices in the system network, which include in the OLT, optical line terminal, or DN, optical distribution network, and ONU, optical network unit, that is from the central office to the end users. This characteristic must be fulfilled by the next generation network providers, so-called next generation PON 2 by the FSAN, Full Service Access Network, or ITUT, International Telecommunication, so that it will coexist with the existing XG-PON 1, EPON and GPON that have already been investing billions of dollars and installed by the telcos companies. This is the element of PON consisting of OLT, that is optical line terminal, located in the provider's central switching office, transmit downstream DS data signal to the ONT optical network terminal at end user, and receive the ONT transmission of the upstream US data signal. ODN, optical distribution network, the physical medium that connects and OLT to its substandard ONU. The ODN is comprised of various passive components, including optical fiber, splitter, AWG, array with guide grating, and optical connectors. ONU, Optical Network Unit, converts optical signal transmitted via fiber to electrical signal at the customer's premises. These electrical signals are then sent to individual subscribers. The ONU is commonly used in the FTTH, fiber to the home, FTTP, fiber to the premises, or FTTC, fiber to the curb application. So OSC, optical splitter and combiner, will split the optical signal into several parts at a certain ratio. Example, a 1:2 50-50 optical splitter and optical combiner combine the optical power carried by two input fibers into a single output fiber. So this is the TWDM-PON. TWDM-PON use the passive optical power splitter at the remote node. 1/n PSC power splitter or combiner is used at the remote node to distribute the optical signal to and from manifold ONUs. For bidirectional TWDM-PON, optical circulators are used. For bidirectional TWDM-PON, optical circulators are used to separate the upstream and downstream signal at the central office and the ONU. In standard commercial TWDM-PON structure, the OLT is connected to the ONU via a 1/32 splitter, and the maximum distance covered is usually 20 km. Advantages of TWDM compared with WDM are that it does not require a complex wavelength management control and that the OLT power requirements are lower. However, the main drawbacks are the lower bandwidth and granularity performance. This is the Wdm Pawn Architecture. Wdm Pawn assigns a wavelength to each subscriber. Wdm Pawn in this context allows the central office to send multiplex signals, each at a different wavelength, to the remote node. The RN remote node in turn contains a wavelength division demultiplexer that passively split the light by wavelength, directing each wavelength to an assigned ONU. Excellent scalability, higher bandwidth, and support multiple wavelengths. Provide protocol transparencies, guaranteed quality of services, and increased security. Wdm-PON has been proposed to be next generation PON and provides high data rates up to 10 gigabit per second. The second generation of full service access network, or FSAN consortium, FSAN/ITU-T protocol would call gigabit capable PON, GPON, or next generation PON2 network to leverage existing PON infrastructure to meet the insatiable need for bandwidth, whereby to support higher bandwidth, at least 40 gigabits in the downstream and at least 10 gigabit in the upstream, to support a longer reach of fiber distance, at least 40 km. Optical distribution network that are typically deployed in GPON today range between 16 and 128 ONUs and allows the coexistence of the network and smooth migration. So TWDM-PON is the next generation access scheme. The full service access network, FSAN group, and ITU are completing the standard that support up to 8 wavelengths, each capable of 10 gigabit symmetrical or 10/2.5 gigabit asymmetrical speed. TWDM-PON to support multiple PON, each sharing its capacity among 16, 32, 64, or even 128 endpoints, depending on the operator's chosen split ratio. TWDM-PON offers 40 gigabit symmetrical in a 4 wavelength implementation, and each wavelength can be designed to different aggregation tasks such as backhaul, business, and residential. TWDM-PON allow wavelength to be shared between operators as part of wholesale agreement. 4 to 8 TWDM channel pairs. Not all need to be active, but pay as you grow. So as a summary of next generation PON, TWDM-PON was selected as the best candidate for the next generation PON2 solution because of its ability to support the next generation PON2 requirement, such as enhanced bandwidth capacity and coexistence with previously existing generation without any change to the optical distribution network. Hence, the research continues on TWDM-PON system configuration with emphasis on tunable transmitter and receiver on ONU, exploiting the cost efficiency that is low capital and operational expenditures, ability to provide 128 gigabit per second up to 500 gigabit per second, 10 gigabit as the present target and 160 downstream, 80 upstream gigabit as a future target for downstream and upstream respectively. Power system budget with energy efficiency, a number of users to support from 256 up to 1024 optical network units, and the longer reach up to 60 to 100 kilometers. So this is the architecture for the next generation PON system, coexistence with the legacy PON. We can see in the CEX, coexistence element block, the existence of all the legacy PON network of OLTs and ONU, optical line terminals and optical network unit. This is research conducted for the proposed TWDM-PON system for symmetric 128 gigabit transmission. In the proposed architecture, we have deployed a low-cost directly modulated grating laser for downstream link and directly modulated laser with a single delay interferometer for upstream link transmission. For working, directly modulated grating laser and directly modulated laser are used as the downstream and upstream transmitters with a tunable range of 3.2 nanometer and thermally tuned to 4 wavelength, separated by 0.8 nanometer. We can see from the wavelength spectrum in the downstream direction and the upstream direction. With this proposed structure, the feasibility study of the MGL at the downstream link, DML and single DI, delay interferometer for the upstream link, the output power, bandwidth enhancement, and power budget results, upgrading to WDM-PON up to a symmetric capacity of 128 gigabit per second using fiber bright grating in optical OLT as a paramount dispersion manager in both upstream and downstream direction. Proven architecture and successful transmission are achieved over 40 km single mode fiber with a power budget of 33.7 dB, which support a 1 to 256 splitting ratio. So we can see from the left figures show the bit error rate performance of the transmission after a 40 kilometer of single mode fiber length for wavelength for downstream signal A and B for the upstream signals. figure at the center shows the bit error rate performance transmission of the system based on single wavelength. For A, downstream signal at 1604 nanometer, and B, upstream signal at 1540 for back-to-back, B2B, with fiber brag rating. After 40 kilometer, single mode fiber length with fiber brag rating, and back-to-back without fiber brag rating. The receiver sensitivity for the case of A, downstream signal after 40 km single mode fiber length with fiber brag rating is minus 19.4 dBm. And for the B, upstream signal is minus 22.9 dBm at the bit error rate of 10 to the power minus 5. And finally, the eye diagram of the signals for back-to-back with fiber brag rating after 40 kilometers single mode fiber length with fiber brag rating and BTB without fiber brag rating for the downstream and upstream cases. So after 40 kilometer single mode fiber length transmission with fiber brag rating, the eye diagrams degradation for the downstream and upstream are acceptable at bit error rate of 10 to the power 5. From the power budget evaluation table with the power budget of 33.7 dB, the proposed scheme's configuration has the highest line rate transmission of 128 gigabit per second and support up to 256 splits over 40 kilometer fiber distance. Next is the research conducted for the proposed TWDM-PON system for symmetric 40 gigabit per second transmission architecture, as shown in the figure, where we have deployed dispersion compensating fiber DCF at downstream and upstream limb and upstream links and directed modulated laser to improve the power budget in a symmetric 40 gigabit per second TWDM-PON system. 4 working DMLs are used as the downstream and upstream transmitters with a tunable range of 3.2 nanometer and thermally tuned to 4 wavelengths separated by 0.8 nanometer. We can see from the wavelength spectrum is the 4 downstream and the upstream direction wavelength. The feasibility study of this DCF and DML output power, bandwidth enhancement, and power budget results minimize the effect of DML chirp and improve transmission performance. Distance up to 140 km with DCF single mode fiber has been realized, indicating sufficient dispersion compensation for TWDM-PON based on DML transmission. Power budget of 56.6 dB and less than 2 dB dispersion penalty. The power budget scheme has the highest value that could support up to 512 splits over 140 kilometer fiber distance. Next are the findings of the results. The left figures show the bit error rate performance as a function of the received power after 140 km of single mode fiber length for 4 wavelengths. The figures at the center show the bit error rate performance as a function of received power after 140 km of single mode fiber length for 1 wavelength. A, downstream signal at 1597.74 nanometer and B, upstream signal at 1444.1 nanometer for 100 kilometer with SOA, semiconductor optical amplifier, and DCF, dispersion compensating fiber. 140 km with SOA and without DCF, back-to-back with DCF and back-to-back without DCF. the receiver sensitivity for the case of A, downstream signal after 140 kilometers single mode fiber length is minus 38.1 dBm, and for the B, upstream signal is minus 38.5 dBm with SOA and DCF at the bit error rate of 10 to the power minus 5. Next are the I diagram of the signal in both directions. After 140 km single mode fiber length transmission, the I diagram degradation for downstream and upstreams are acceptable at bit error rate of 10 to the power minus 5. From the power budget evaluation table, the power budget for the downstream and upstreams direction among the transmitted 4 channel are 56.6 and 56.8 dB. So the proposed scheme of 40 gigabit per second TWDM-PON architecture support up to 512 split over 140 km single mode transmission distance with the estimated power budget of 56.6 dB. So there is much more option for the current research on the area of next generation PON 2. The other option is using optical code division multiplexing PON, or is OCDM-PON, optical frequency division multiplexing PON, or FDM-PON, and WDM-PON. And again, study on the components at the OLT, ODN, and ONU, and leverage technology developed for efficient TWDM-PON system in terms of data rate and power budget system at a sustainability at substantially lower cost for moderate reach system by utilizing direct modulated transmitters instead of external modulator alongside a simple direct detection receiver. This can be done based on the modeling and simulation as well as experiment. And for the future outlook on the TWDM-PON is the integration of both optical as a network and wireless access network, which is the hybrid optical wireless access network. To further increase the capacity, the advanced optical transmission technologies such as partial division multiplexing or SDM are based on multi-core fiber. Future reconfigurable TWDM-PON system for achieving a flexible TWDM-PON such as flexible transceivers, flexible optical switches, flexible grid, dynamic wavelength and bandwidth allocation, and dynamic bandwidth allocation. To meet that, a reality software-defined network could be performed through elastic optical network to manage the resource efficiently. In conclusion, the modern impetus for the telecommunication with carrier wave at optical frequencies owes its origin to the discovery of laser in the 1960s. With a system that used glass fibers as the transmission medium and light wave as carrier wave, it is distinctly today to have 130,000 simultaneous telephone conversation. The photonic device-based optical waveguide enables low-loss light propagation. The photonic device-based optical waveguide enables low-loss light propagation. Photonic device based on polymers meet anticipated future requirement for ultra-fast and ultra-high bandwidth communication up to the terahertz region with low power consumption. Polymer photonics become additive and important for integrated photonics with the III-V semiconductor materials. An integrated photonics platform are to go hybrid with the introduction of innovative materials specifying polymer technology such as TO and EO polymers materials, electro-optics and thermo-optic polymer material. Passive optical network offers favorable optical access network for significantly enhancing the bandwidth of access network. Today, TWDM-PON was selected as the best candidate for the next generation PON solution because of its ability to support next generation PON 2 requirements, such as enhanced bandwidth capacity and coexistence with previously existing generation. Hence, the research continues on the evolution of PON system configuration with emphasis on coexistence of the evolution of PONs towards next generation PON. Speed of data rate as future target 160 for the upstream for the downstream, and 80 gigabits per second for the downstream respectively. Power system budget with energy efficiency. Number of users support from 256 up to 1024 optical network units. And finally, long reach up to 60 to 100 kilometers. For the future likely attributes, optical networks look set to become the standard as we head towards the era of optical network. Optical connection will soon be between boards and even on chip, as well as at the network level. Hybrid technology with the integration between optical wireless and optical networks, and finally, optical network management and control will be more efficient and flexible. With that, I end my presentation, and finally, my dedication for the Professorial Inaugural Lecture today. I would like to dedicate my sincere thanks and gratitude to my family, my students, my colleagues at Lightwave Communication Research Group, my colleagues at the School of Electrical Engineering, my colleagues at the Faculty of Engineering, my colleagues at the Office of Research Alliance, to all Deputy Vice Chancellor's Department, Vice Chancellor Office, and all of you that have supported me for the career endeavor at UTM. Thank you very much. Jazakumullah khairan kasira. Thank you.
Alhamdulillah. Thank you very much, Prof. Abu Sama, for enlightening us with the very informative and inspiring lecture. Okay, from the lecture, we learned on how photonics technology can be used to eliminate the electronic bottlenecks, given its high frequency in the terahertz range, very low loss, and enormous bandwidth. It is hopeful also that the photonic-based devices will be made widely available in the future, as this will further facilitate high-speed and larger capacity telecommunication networks, such as the next generation PON 2 and all-optical networks. And this will greatly benefit our society and the whole mankind. Okay, now I would like to invite Professor Engineer Dr. Sylvia Mahdaliza binti Idris Sultanameh, who is also the Deputy Dean of Development and Alumni, Faculty of Engineering, to review the professorial lecture. Okay, over to you, Prof. Sylvia.
All right. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. And very good afternoon, everyone. Thank you, dear MC, my dear friend, Associate Professor Engineer Dr. Nadia, Chairman of the Professorial Inaugural Lecture, my boss, Professor Technologies Dr. Ruzairi Abdul Rahim, Dean of Faculty Engineering, UTM, academic colleagues, industry partners, friends, students, ladies and gentlemen, here at this hall, as well as wherever you are on the globe. Thank you, Professor Abu Sama, for giving the Professorial Inaugural Lecture today. Congrats anyway. The title, Photonic Eliminating Electronics Bottleneck. Very inspirational lecture indeed, that focus on the guiding light into semiconductor nanostructure that revolutionize the concept of photonic device, offering a practical pathway towards next generation power efficient optical network. I'm honored to be invited by Professor Abu as a commentator on his professional inaugural lecture today. At the same time, I also feel proud of him as my colleague and mentor. He was my supervisor once upon a time, way back in 1998 when I took an optical wireless communication project for my final year. Project undergraduate under his supervision. Alhamdulillah, on top of that, he was my academic advisor, and I had taken 2 courses with him. It's been an utmost honor to be his student. Professor Abu Sama has taught us in the most friendly way. He is a very popular lecturer in UTM, and in his class, especially for EMT, is always full. I really admire on that. And indeed, he is a very inspirational person, great teacher, mentor to many. MashaAllah, we have been working together in this photonic technology more than 2 decades. Alhamdulillah. I truly appreciate you and your support in many occasions to many members in the photonic community. Get back to Professor Abu's professional inaugural lecture today, titled Photonics Eliminating Electronics Bottleneck. And I think I really thank you, Prof. Abu, for great sharing and valuable knowledge on important topics to the public today. Optical communication technology, dear audience, here at this hall, as well as everyone out there around the globe, I believe by listening to his lecture today, just now, you realize that all of us are connected through light. We are connected through light, supported by photonic technology. You can feel that Prof. Abu lecture in UTM streaming via 1,000 kilometers of fiber optic around the globe without any hiccup in real time. In the last decade, we know the technology are emerged, as well as optical communication technology advances. Electronic circuit increase in complexity and performance. The increase also require an increase in the number of interconnection per chip and interconnection speed. Otherwise, the bottlenecks due to electrical connection created will limit the overall system performance. We want to make sure everyone are connected and feel the services in comfortably. The interconnection include a chip-to-chip module on the common multi-chip module, a multi-chip to multi-chip module, and also board-to-board communication through backplane. It's very difficult for me to explain how is it, but in terms of the increasing cost, in terms of power, size, component, count, weight, and also reliability of implementing the required interconnects electrically, has motivated serious consideration of replacing electrical interconnects with optical interconnects in optical communication network. Because the demand of the user, the demand of the everyone with the service. In the last decade, however, an interesting revolution has been occurring in the world of optical communication in this area. The major technical issues are now shifting from those of optical link to those that actively control signal path through various information distribution. This interest has been triggered by explosive growth in high data rate multimedia traffic over the past few years. You know, right? Every day, everyone are connected through WhatsApp. 24 hours with the Facebook, IG, and many things nowadays are really different compared to the last 10 years. That's the reason the interest has been triggered by the explosive growth in high data rate multimedia traffic over the past few years. Increasing user demands for the high performance connection and expanding the number of users has initiated the development of fiber to the home or fiber to the hub system and local area of metropolitan area networks. This pandemic, COVID-19 especially, you can feel everyone are connected must be connected. Everyone have to work at home. Yeah? Everyone have to deliver their job through internet, and that internet backbone is actually photonics. That's the thing that I would like to share, and this general knowledge should be understood, everyone, so that the work can be focused, because light wave transmission must be low loss, low dispersion, single mode fiber has become the choice for high capacity point-to-point communication system. From the viewpoint of transmission, fiber offers the potential of enormous information bandwidth. To preserve this advantage in future light wave network, it is important that the total information capacity of the network not be limited by the switch, which is the electronics that provide connectivity. Recap from the Prof. Abu lecture just now, you can recall, it's quite technical, but the one that I would like to highlight here, the current optical cross-connect use an electrical core for switching, where the optical signal are first converted to electrical signal, which are then switched the electronic switch and finally converted back to the optical signal, or in other words, optical to electrical to optical switching, which is quite complex, but that's the technology available back then, or further transmission, for further transmission. Therefore, electronic switching device have limitation on both the data rate that they will handle and the switching reconfiguration rates achievable. So the main attraction of optical switching, which is the key research and the key project of Professor Abu back then during his PhD, is that it enables routing of optical data signal without the need for conversion of electrical signal, or sometimes referred to all optical cross-connect. Now we are all optical. Only that maybe at the distribution network, yes, there are electronics optical. The contrast to OEO, which is optical, electrical, optical, when the data rate increases, the expensive transceiver and electronic switch core have to be replaced. And the all optical is independent of data rate and ready for future data rate upgrades. We are ready for that, and all researchers working for that. Since there is no need for expensive and power-hungry high-speed electronic switches, transmitter and receiver, the system becomes less expensive. In addition, the reduction of the complexity improve the reliability of the all-optical cross-connect compared to optical, electrical optical solution. The key component for all-optical cross-connect is photonic switch, which is a key contribution of Professor Abu Sahmah. Photonic switches are attractive component for routing of high bit rate optical signal in all optical network, for circuit protection switching to bypass a faulty system or cable, and for the space stage of transparent optical cross-connect. Switching of cable TV at your home, in local area network, high bit rate data in optical backbones of a computer and optical signal in sensor, maybe further application in the telecommunication area. Photonic switches suitable for the above mentioned application could be implemented at low cost by using polymer waveguide technology. It's a big project of Professor Abu previously. As mentioned by Professor Abu lecture, most of the photonic switches that has been researched and demonstrated, such as directional coupler, wide branch or digital optical switch, multimode interference and multimode interference Mach-Zehnder photonic switches, are all based on polymer material. Because of their low cost and high speed possibility, as well as fabrication flexibility, dear friend, there are many jobs down there in photonic that we as a researcher should continuously explore and work towards that. As mentioned by Professor Abu just now, for high-speed device, a good speed match between the traveling electrical signal and the optical signal is very important. The closer the two speeds are, the longer the interaction length and the more effective the modulation. A large bandwidth length product is required for the material to be used for fabricating the high-speed switches. This technology, it sounds complex. Yes, it's really complex and it requires a huge amount of investment. So that, because a low dielectric constant is desirable for high-speed devices because it reduces the response time of the device by reducing the capacitance of the electrode. Professor Abu has touched on the challenge of the future access network of passive optical network PON. I can see there is a few questions coming up from the Facebook. Let him to answer that. With the emphasis of coexisting and maintaining the investment of the current EPON and also GPON, of the evolution of PON towards next generation PON, since most telco service provider invest multi-million dollar to deploy PON system, we here in Malaysia, we enjoy the facility in their network. This has been done is by using the existing optical distribution network and avoiding the usage of the same wavelength allocated by current PON technology. Time and wavelength division multiplex passive optical network, one of our key research work previously, trend is considered as the most extraordinary trend of the next generation solution to accommodate exponential growth of the traffic for converged new services. This is the only promising solution for future terahertz communication. This within this couple of years, there is no many real-time services required by people, by human. Human is really hungry with the facility of very good communication. He also has proposed, I would like to highlight one of his contribution. Prof. Abu has proposed to use optical dispersion compensation based on the widely deployed dispersion compensating fiber. I'm sorry, it's quite complex name on that topic. Optical line terminal OLT and employing directly modulated laser to improve the power budget in symmetric 40 gigabit per second time wavelength division multiplex passive optical network system. Congrats, Prahabu, on that. In other work, I would like to highlight, he has demonstrated a cost-effective way to upgrade TWDM-PON up to symmetric capacity of 128 gigabit per second using fiber gratings in an optical line terminal, which is as a paramount dispersion manager in high-speed light wave system in both upstream and also downstream direction. This low-cost and potential chipless directed modulated grating laser is employed for the downstream link, and directly modulated laser with a single delay interferometer is employed for the upstream link. It's demonstrated, the findings show that a successful transmission is achieved over 40 kilometers single mode fiber with a power budget at 40 dB. Please, everyone, our student out there, researcher out there, please search Prof. Abu publication to read more on his finding and contribution. Feel free to contact me if you need assistance. I have all his copies. All right. Looking further into the future, with the breakthrough in scientific progress and solving technical difficulty, photonic devices and networks look set to become the standard as we head towards the era of all optical networks. All light, at the device level, optical connection are already used within chassis, but with soon as common between boards and even on chip themselves. At the network level, optical connection will be used to connect the network devices to people home, to you there. It's already connected, and even connecting between people and things, which is IoT technology. IoT technology really needs good backbones of all optical networks. Prof. Abu also highlighted that the TWDM-PON system is one of the future solutions, and will expect that the door is open for additional innovation and ingenuity in this technology. We really welcome everyone here to embark in this journey, to be with us, to work in this research, and encourage additional research in this developing and significant field. It is indeed an important milestone for the research work conducted by Prof. Abu and the team in Lightwave Communication Research Group. I'm really proud to be part of his team in terms of photonic devices and networks in the context of academia, where the expertise gained is very significant for technological advancement and talent management in this area. My final remarks on this would be my utmost hope that Professor Abu Sahmah will continue to contribute his expertise. He's still young indeed, valuable experience to UTM and nation. I know, he said to me yesterday, he will retire in a couple of years. However, given that he is a great asset to Malaysia, I wish he can still serve the academia and industry for many years to come. Very healthy man anyway, to be retired at 60 kind of a big loss to photonic community. Because of Professor Abu Sahmah are an incredible professor with high knowledge of both wisdom and great study. With that, I end my commentary of the Professorial Inaugural. It's very difficult to pronounce this word. It's very important to us. By Professor Engineer Dr. Abu Sahmah on Photonics, Eliminating Electronics Bottleneck. All the best to Professor Abu Sahmah. May Allah reward Prof. Abu and family abundantly with the highest level in Jannah. Amin. Thank you very much. I pass back the mic and screen to the MC, Dr. Nadia, inshallah. Thank you very much, everyone. Alhamdulillah.
Okay, Alhamdulillah. Thank you, Prof. Sivia, for the excellent review on the Professorial Inaugural Lecture, including Prof. Abu's achievements in the area of photonic devices and next generation PON. I believe we can get many useful inputs from Prof. Abu Sahmah's background profile in order to become an excellent asset to the organizations that we work with by building up on our expertise and skills. Okay, so now I would like to open the floor for the feedback and Q&A session. Okay, let me start with the first question. Prof, how do you foresee the future of photonics beyond application in the telecommunication field? Hi. Prof. Abu?
Can you repeat the question?
Okay. First question from MC. How do you foresee the future of photonics beyond application in the telecommunication field?
Okay. How do you foresee the future photonic beyond the television? I think there is a lot of photonic application already exists today, and possibly more sophisticated devices will be produced in the near future in the field of other than telecommunication. For example, in the military, where in the military we have photonics is the enabling technology in the security and defense sectors. The most important is photonic is super lightweight, and then of course the beauty of photonics is low switching power, because we are using laser or light emitting diode with the very low power consumption, 1 milliwatt, and then we can still detect this low power in nanowatt level, still can be detected. And then of course laser, because of small line width, even LED also smaller line width. They call it a line width instead of the spectrum, the output spectrum of the laser or LED. They call it as a line width because it's very small. So meaning that the smaller footprint, and of course because of low power consumption, and with in military, I think a lot of power needed, so a lot of bulky equipment needed, so hopefully minimal cooling requirement is needed. And another field like in medicine, for example, X-ray, we have X-ray, MRI, computed CT scan, and recently we have LASIK. So I think all these like LASIK, X-ray, and CT scan, they are using photon, using photon to interact with the human body. So new optical sources for biomedical optical instrumentation interaction method will provide, I think, remarkable increases in sensitivity and as well as in precision by using and again also because of the we are using optical photonics laser and sources, so non-invasive and low cost method. low-cost method to obtaining, I think, and also preventing disease, and we will greatly reducing the cost of treatment and improve health and improving the quality of life for the patient. And I think the most another field, other than telecommunication is the optical sensor. I think very important for structural health monitoring in the field of civil engineering, aerospace, marine oil and gas, and etc. These optical sensors might prominent in the near future for the photonics. Thank you.
Okay, thank you for the very insightful answer. So we can see that there are more potential applications to be explored in the future. Okay, so maybe you can have some questions from the FB. Okay, let me read the first question from Madam Afida M. Zain. Assalamualaikum, Prof. My question is, what do you foresee the challenging future for telcos companies in Malaysia? I think we all seek Prof. Abu's wisdom, so that's why so many questions on future, foresees.
I think like what we have discussed in my talk just now, that telcos companies must make technology investment. Yeah. For example, in my talk that I delivered just now, the challenges for future access network or passive optical network, for bandwidth requirement, demand for higher bandwidth and quality of services, must achieve high capacity and good scalability in terms of link range and number of users. So most telco service providers already invest multi-million dollars to deploy PON system, like Ethernet PON or Gigabit PON in their network. So to maintain the investment of the current network, the evolution of PONs, passive optical network, next generation PON must be able to coexist with the current PON. We have seen at what time, for example, the future for the telcos company in Malaysia was brighter than the sun for telecommunication company. When we see in 1990s, for example, all allow us to have a mobile telephone, a very, very small device, and we keep on short message service, SMS, so which I think become very popular at that time. And then to meet that demand, telcos company used to build 1,000 of cell tower in every district, I think, and to connect the country, expand the coverage, and to woo millions of subscribers, millions potential subscribers to the wireless communication world. But and then came mobile internet, 3G. 3G. I think this telco company also further enhance telco's presence. But recent years, when I think the telco's prospect have suffered due to technology and application that got to connected the world. When the technology of 4G, LTG, where we have the apps of WhatsApp, for example, WhatsApp and voice call using WhatsApp. So I think the widespread use of messaging of traditional voice call and the SMS, I think become obsolete. Okay, because of that, telcos lost, I think, billions of dollars traditional revenue from the SMS and the voice call. people have moved to the WhatsApp and calling also using voice apps. So that's why I think important to telcos company to make investment, at the same time also ponder about devising might be business model, especially with the emergence of 5G, and very near we will have 6G. Might be some of the content and also the infrastructure should be shared among the telcos companies, okay, so that they can in terms of devising the business model, not only rely on the technology. Some technology might obsolete, but I think also regulators should play also a role, like for example, like ITUT, International Telecommunication Union, for telecommunication. They have to make sure for the next generation PON 2 have to coexist with the next generation PON 1, meaning that because of the telcos company has already invest billion of dollars, multi-million of dollars, so they should the legacy of that next generation PON 1 should be there, and then they have to fulfill this for the next generation PON 2. And in case of Malaysia, I think we have MCMC, who are the regulators, to the any related to multimedia industry. So maybe I think MCMC could play a role, like ITUT, might be to like a what we call it as a refarming exercise of the spectrum. For example, maybe we have to go to the lower spectrum so that the coverage area will be bigger, and this also can penetrate building. When we go to a lower frequency, meaning that the lambda is higher, so they can cover bigger area, then the penetration depth also in depth, so can cover through building. Maybe this two kind of thing. So that's my answer. Thank you.
Okay, thank you very much, Prof. So next question, okay, from Madam Fadila Atan. Salam, Prof. I have a question concerning the issue of cabotage policy and submarine optical cable that has been buzzing recently. How long is the submarine cable actually in our country? Okay, so this is
I
related to
will not
recent
respond.
issue. Yeah.
So I think I will not respond to the issues in question. But what I can respond is that so in our country actually we have two bodies who govern this telecommunication. One is the telcos company, Telecom Malaysia. That is a corporate company. After privatized, they become the company, telcos company. Telecom Malaysia is a provider of national connectivity and digital infrastructure, and the other is the Malaysian Communication and Multimedia Commission, MCMC. This is the regulator for the communication and multimedia industry. Before it's JTM, Jabatan Telekom Malaysia. We have two, Telekom Malaysia, Jabatan Telekom still maintain, but then they change to MCMC, but still under government. So MCMC is under government, that is a regulator. And the telcos company like Telekom Malaysia. So the first submarine cable was deployed in Malaysia in 1995. And it is connected between the peninsula, landing in Kuantan to Sabah at Tanjung Aru. That's one 1995, deployed 1995, and then the lifespan normally for the undersea cable, submarine cable is for 25 years. So already finished, already taken, replaced by the new submarine cable that was launched in 2017. That connect also Peninsula Malaysia and Kuching Sarawak, which is more span about 3,800 kilometers. Okay, that is the second. And then the submarine cable can support up to 100 gigabits. And for your information also, the initial capacity for this second link of submarine cable is 4 terabit per second, and can be upgraded to until 12 gigabit per second in the future. Okay, and then I think what I can comment about the sabotage issues. So we have My Digital actually, My Digital. What our aim is actually is to be our aim is to have more marine submarine cable. By 2025, Malaysia we have the longest and many submarine cable, but I think it will not achieve because of this sabotage issues. But not the political one, but this one is for the yeah. Okay, I think I can answer for that. Thank you.
Okay, thank you, Prof, for sharing a more practical aspect in the context of our country. So we hope a win-win solution can be found that benefits Malaysia. Okay, all right. There's so many questions in Facebook. Maybe you can have our last question. Okay. I have one question for Prof. Abu Sama. What do you think of the roadmap of optical communication in the future? Okay, again, a question on
roadmap. We have to have a workshop ni kan nak buat roadmap. Tapi what I think what I've mentioned, in the future outlook of TWDM-PON 2, I guess hybrid optical and wireless access network. There is the integration. Might be the roadmap integration of both optical access network with the optical and wireless, or might be integrated, become hybrid. And then also, as I mentioned in my option of research, future outlook is the SDM instead of WDM. Maybe in terms of technology of the modulation itself, there will be a space division multiplexing, based on multi-core, fiber. And this will increase the capacity, can go up to, now we are talking about terabit per second, maybe to petabit. From tera to peta, then to exabit, to 10 to a power of 12, 14, 15, 18 petabit with this new technology, modulation, and the multi-core fiber, MCF, using space. And as mentioned by Prof. Sivya just now, OOO, all optical network. Maybe in the future we'll have become a standard, all optical. There is no more conversion anymore to electrical, because we are talking about very, very high frequency. So electronic cannot support anymore. Okay. So, and maybe in the future also we'll have roadmap is optical antenna. Have you heard about that? Optical antenna, we have electromagnetic antenna, right? Maybe in future we have optical antenna. And also maybe a VLC. Now we have seen, many, even in UTM also, we have changed all the fluorescent lamp with the visible LED, light emitting diode lamp. Instead of using it as illumination, we also can use it, because LED, we can use it as a transmission medium. So maybe this VLC could replace or augment Wi-Fi technology. So in a room, when we have all the visible light, so instead of using it as illumination, so we can also use it as a transmission of the signal, LED. So might be the augmented, not to say to replace, but augmented to Wi-Fi technology. And finally, might be FSO also, free space optic that has been mentioned by Prof. Sivia in his last lecture, radar, based on FSO, free space optic, whereby especially in the urban area where there is no lot of buildings, so we have no space to dig dig the fiber or coaxial cable. So maybe we need to use free space optics. So just transmitter and receiver put on the up the building, onto building. So might be a trenching of the where trenching for new optical fiber might be would be costly, or to spend river, in the urban area. So maybe FSO. I think if I can summarize it, Dr. Nadia, thank you.
Okay, thanks, Prof. Okay, one last question, really last question from Facebook. From Ali Osman. Okay, this is in Jawi. The capital expenditure capex cost for fiber optic communication is less than the conventional coaxial system, since my understanding is that the fiber optic cable itself is much more expensive than the wire cable.
Okay, thank you. Okay, yes, the construction of optical fiber system, of course, very expensive. Even the fiber itself, fiber optic itself, is more expensive than the coaxial cable. But we are now talking about the amount of capacity, information capacity that that the fiber optic can carry. That is much more higher than coaxial cable. So when we are comparing in terms of the amount of channel capacity that the fiber can carry compared with the coaxial cable, so as a whole, finally, the construction cost of fiber is less than the coaxial cable. We are not comparing about the price. We are comparing about the amount of information that the fiber optic can carry. Okay, so per channel optical fiber, of course, will much lower. Per channel optical fiber, one channel optical fiber might be can accommodate thousands of voice signal, but for the coaxial cable might be 10. But in terms of when we do construction for that fiber based system, of course, expensive. But now we actually, like today, we are actually selling bandwidth, like Telecom Malaysia. They are selling bandwidth. When you buy Wi-Fi, and then some Wi-Fi is 100 ringgit, some 50 ringgit. What actually they are same application, but they are selling the bandwidth, the data rate that you use, and then might be 400 kilo, 10 megabit, 100 megabits for small office is 300 megabit per second. So meaning that the channel bandwidth costs money. So similarly with the optical fiber and the coaxial cable. Okay, I hope this will help, will answer.
Yeah, right. Okay, thank you, Prof. That's the last question from Facebook. And one final last question to close this Q&A session is, out of curiosity, is there any potential technology, Prof, that can replace photonics? What do you think?
Fundamentally, as I mentioned, there is no other thing that is as fast as the light, right? That can travel. The fastest is light. The velocity of light is 3 times 10 to the power of 8, 300,000 kilometers. So there is no other thing that we can find as fast as light that can travel. So in terms of transmission medium, I think there is none. Something can replace photonics. But might be Prof. Sapian is here. New material will come up. I believe. Otherwise, Prof. Sapian will be angry, because he's a father of manufacturing. Yeah, we are looking after the new material. Yesterday also we have a Benkel workshop about the future in 2040. What kind of material to make a robot, so we have to think about the new material. But even today we have seen graphene. Graphene is a new material that can I think not to say to replace, but to be hybrid, because graphene is based on plasmonics. So photonics. This one is plasmonic. We have heard about the plasma TV, right? So graphene is a very thin layer of materials, but when we can hybrid it with the photonics, silicon photonics, with integration, so they will emerge as a graphene plasmonic. And so graphene plasmonics, I think will impact all sectors, I think, which include even optoelectronics, graphene. Now, I also have evaluate some of the PhD theses. They are using graphene for some of the for sensors, optical sensors, photonics, and semiconductor. So I think yes, might be, and then of course because of might be compact size, lagi compact size, fast speed. I think yes, might be in terms of devices. Yes, might be. Dr. Nadia, yeah.
Yes, thank you. I'm satisfied with the answer. All right, so with Prof's answer to the question, finally we have reached to the end of today's program. I would like to apologize for those questions in Facebook that are not answered. It will be answered later, inshallah. So do check out the post to read the replies. Huge congratulations to Prof. Engineer Dr. Abu Salma for his success, and thanks for the wonderful lecture and sharing session. I also want to thank the chairman, Prof. Technologist Dr. Ruzairi bin Abdul Rahim, and the reviewer, Prof. Engineer Dr. Sivia Mahdaliza binti Idrus Sultaname. And also much appreciation to the organizer and committee who have worked hard to realize the event. And not forgotten, I want to highlight here at the moment we have 500 FB engagements and 1,400 viewers. Okay, so congratulations again to the Faculty of Engineering, the organizers, and thank you very much to the viewers for staying tuned with us within these 2 hours. So before we leave, let's recite Tasbih Kifarah and Surah Al-As as we seek for Allah's mercy and forgiveness for our mistakes and sins. Okay, subhanakallahumma wa bihamdika asyhadu an la ilaha illa anta astaghfiruka wa atubu ilaik wa a'udzu Okay, so see you in another lecture series by UTM. Assalamualaikum warahmatullahi wabarakatuh and have a great day. Okay, bye-bye.
Jazakumullah khair.